All right, so we have this circuit up and running here in the PhET sim. Feel free to play around with this and build these as you like. They're pretty neat. We're in the intro section. But what I'd like to point out real quick is that you can use a couple of different meters to measure what's going on here. If you grab a voltmeter, you can simply pull it off of the side over here. And what I really want you to think about is when we talk about voltage, we're speaking of the difference in energy from one place to another. The difference in energy from one place to another. You notice this voltmeter has two probes, these wires sticking out of it, and we can put them different places in the circuit. And the most logical place to put them might be on either side of the battery. If you put a voltage probe on one side, you don't get anything until you put the other probe on the other side. Boom! And it tells us this particular battery is a 9-volt battery. By the way, it's a sim, so you can adjust that. But if we simply put the probe across the battery so it shows one side to the other, you'll notice that. What do you suppose happens if we put the voltage probes on the same side of the battery? If we put the probe right here, now it says 0 volts. Well, that's because it's looking for the difference in energy between the two places we connected. 0 volts there, but as we go to the other side of the battery, we see 9 volts. Now, anywhere throughout the circuit, if we compare, we'll get 9 volts because there's 9 volts of energy per charge added to the circuit by the battery. Sorry, I shouldn't have moved that. But as I move this probe around, you'll notice it stays at 9 volts, 9 volts, 9 volts, 9 volts. But then as the energy goes through the light bulb, what happens to it? Well, you'll notice it comes off as light, this lovely halo. So when I measure the voltage on the other side of the light bulb, boom, you'll notice now it says 0. And that's because there isn't a difference in voltage anymore because I'm touching the same parts of the probe. So again, on the other side of the battery, 9 volts. We've got 9 joules of energy per charge. But after the energy goes through the bulb and gets dumped off to light and heat, now we're back to 0. So just by leaving the negative probe in place and moving the positive probe around, you can see changes. Now, what if we hook them up the other way? If we put the negative over here, well, it says 0 again. But if we put the negative there and I put the positive on the other side, hey, now it says negative 9 volts. Why negative 9? Well, that's because the difference from this point to that point is the reverse. The charges go in the opposite direction as my probes, and that sign tells us negative. We can simply take the probe and put it on either side of the bulb. Again, if you'll notice, if I put it on either side of the bulb up here, it'll show us positive 9 volts because the positive probe is on the positive side. But if I flip it around and put the probes in the other position, hey, we'll notice now it's negative. So again, the voltage meter, or the voltmeter as we often call it, is a really useful tool, and it helps you to see the difference in energy per charge. Something you can tell really nicely from the sim is that the flow of charge follows a single path. We measure charge flow with a device called an ammeter, and it's a little bit different to hook it up. This isn't actually what it looks like in the lab, but we're going to use this because it works well. This is like a little detecting unit. And the point is, if you put this ammeter anywhere there's current flowing, boom, it'll tell you how much there is. So if I put it right on top of the wire, it'll tell us there's 9/10 of an amp of current. And the point I want to make is as we move it through the circuit, you see the very same number everywhere. That is, the same current leaves one place, travels around, and comes back. That's the only option if there's only one path for the current to flow through the circuit. What I'd love it if you could do is play around with this a little bit and just experiment with the circuit. Now, you could make it more exciting by putting in multiple bulbs and multiple batteries and all sorts of things, but I'd love it if you'd play together with these meters. Finally, I want to ask you to recognize how these ideas come together. Hey, what is the charge per time called? That's called current. And what is the cause of current? Well, current only flows because of voltage. Current happens because of voltage. But the amount of current that flows depends upon what you're putting the charge through. Again, if we go back over to the circuit and we break it open a minute and we add a second bulb, do you remember how much current we had? I believe we had 0.9 amps. If we put a second bulb in this circuit and we check the current again, do you suppose it'll be more or less? Well, you can tell by the arrows there's a difference in the motion. And if we have more bulbs, hey, look, the current went down. In fact, you notice it went down by a factor of 2. Well, the ability of charge to flow through something indicates how much current will flow. And as we add more bulbs, it gets harder and harder for that to happen. That concept is called resistance. Resistance is a measure of how difficult it is for charge to flow through an object. Of course, generally a conductor, but conducting versus insulating isn't really a one or the other kind of thing. It's more of a continuum from really good conductors to really lousy conductors. And the way we measure that is, again, this concept called resistance. So we're going to write this with symbols. I for current, as you know, V for voltage, and fortunately, very logically, R is the symbol that we use to represent resistance. This relationship is a fundamental relationship we use for electrical circuits. It works really nicely, that current is voltage divided by resistance. Again, let's check the units. Amps. Now, this is not what we saw before. We saw amps were coulombs per second. Well, that's how we define an amp. But what's the cause of current? Well, the cause would be a voltage being provided by an energy source. And what affects how much that voltage causes current to flow is what's called resistance. Now, I just drew a funky letter right there. Time out. Let's talk about resistance. So resistance is a measurement of how easily charge can flow in a circuit. Resistance, a measure of, well, really, it's how difficult it is. A good definition would be difficulty of charge to flow. Sorry, that's hard to read the word resistance. But the units that we use are called ohms, O-H-M-S. Resistance measured in ohms. And the unit has a symbol that looks like an upside down horseshoe. It's the Greek letter omega. Resistance in ohms is omega. And again, when we use this relationship, it's going to be super handy, and it's really pretty easy to deal with. It involves current and resistance and voltage. The name of this resistance equation, or this circuit equation, is Ohm's law. As you set out to try to solve some problems today, what I want you to recognize is all you're doing is using this 3-variable equation to turn around and solve problems. You can solve it 3 different ways, right? We've solved it here for current. Now, if we turn around and solve it for voltage, the nice thing is the fraction goes away and we get V is I times R. And in the third case, we can turn around and solve it for resistance. And when we do that, we see that resistance is voltage divided by current. So there's 3 different ways to use Ohm's law. And as you set off today to tackle some problems, I want you to recognize that that's the tool. Hey, thanks for thinking about that. Let's see how it goes.